Got it. Ay, mira, esa Alicia Sun se parece a mi amiga la...
Hello, everyone.
Hi, Alicia. How are you?
I'm doing well. How are you?
How are you? I am Paola Iturri.
Okay.
I assistant administrator of Aporta. I am not student. Please, we start the session at 7:10 o'clock, please.
Okay, yeah, sure. Maybe I can just go ahead and start because I saw like, are we waiting for like more people or?
Okay.
Okay. Maybe just like maybe 1 more minute so we can get started.
Perfect. Thank you.
All right. So I think we can maybe start because we have like a lot of material to cover for today's session. So hello everyone. My name is Alicia. I'm a PhD student at MIT, and I will be teaching tonight's review session for the fundamentals of statistics. So first I'll go over like the topics we'll be covering today. So first we will talk about like asymptotic results, which include modes of convergence, the law of large numbers, and the central limit theorem. And we'll also talk about statistical models and estimators, as well as the properties of common estimators. Then we'll also go over a little bit confidence interval and delta method. Then we'll talk about like probably the most important estimator in this class, which is a maximum likelihood estimator. Then like if we have like a little bit more time, we'll talk about hypothesis testing, linear regression, as well as generalized linear model. So in this course, you'll probably see like a lot of like asymptotic results, which just like states like some theorem in terms of a really large sample size. The first one that you will keep like encountering this course is the modes of convergence. So basically, we have 3 types of convergence that you will encounter in this class. So the first one is almost surely convergence. So this is like what we have. Sorry, this should be the strong law and this should be weak law. So the almost surely convergence is what we have in the strong law of large number. So this one it's will be like more abstract, but it's basically assume that if we have a sequence of random variable xn, and this should be equal to if it converges almost surely to a random variable x, which means that this two variables should be the same on some subset of sample space omega, and this sample space is like belongs to like a space A, and the probability of this event should be equals 1. So this is like the definition for almost surely convergence. The second one we have is convergence in probability. So this one essentially just requires that the probability of our sequence of random variable xn minus x should be greater than epsilon. The probability of this thing should equals to 0 for any epsilon greater than 0. The last one we have is convergence in distribution, which requires that the CDF converge to each other. So basically, if the CDF for xn is fn, and the CDF for the limiting variable x is fx, we just require that these two CDF converge to each other. So these three types of convergence are has a different hierarchy of their strengths. So basically, in the hierarchy of convergence, we would have almost surely convergence would imply convergence in probability, and convergence in probability would imply convergence in distribution. So now, like in this course, we talk about like a lot of counter examples where we know that the converse of this won't necessarily hold. So this type of convergence results will be like used a lot in the law of large numbers as well as CLT. So law of large numbers use convergence in probability, which basically says that the sample mean, which is just 1 over n summation from x1 to xn, should be converged in probability to the population mean mu. So this is like the law of large number. And this is a weak version. And in a strong version, we have this thing converge almost surely to the population mean. But in this course, we'll mostly use the weak law of large number. And this, so the law of large number tells us like the limiting behavior of the sample mean. And then the CLT tells us something that's like about the distribution of this limiting variable. It's a distribution of the sample mean around the population mean. So CLT states that our sample mean minus the population mean times the square root of n should converge in distribution to a normal random variable with mean 0 and variance sigma square. So this is like the most important points for this part. So the next topic I want to review is a statistical model and an estimator. So remember, like the way we define like a statistical model is three components. The first one is the E, which is a sample size. Then we have a family of distribution defined by its density function p theta. And then the last component is the parameter set, which is denoted by theta. So this is a distribution family. So after we define a statistical model, we can there are different properties of the estimator. So the first so the first thing we want to know about statistical model is like whether the parameter of the statistical model are identifiable. So identifiable just means there's like a injective mapping from the parameter theta to the distribution family p theta. So in other words, this means like if there are two theta which theta and theta prime, where theta doesn't equal to theta prime, we should expect that p theta also doesn't equal to p theta prime. And so after we have a statistical model, we can try to find an estimators for the parameters. And there are like a few important properties about the estimators. So the first one is unbiasedness, which says that the biasness of an estimator is measured by the expectation of the estimator minus the true estimator. So that if this equals to 0, we say that this estimator is an unbiased estimator. The second one is consistency, which states that our estimator, as the sample size increases, should converge in probability to the true parameter theta. And the third one is asymptotic normality. So this is like a very important concept in this course, which essentially just states that the estimator sigma hat minus the parameter sigma times the square root of n should converge in distribution to a normal random variable with mean 0 and sigma and the variance of the parameter theta. And another thing will be useful is the quadratic race. So quadratic race is defined as the expectation of theta hat minus theta squared. So this is like in the language of like machine learning, this is also the mean square error. So this, if we break this up, this would like equals to the variance plus those plus the base square. And I think in the PSAT or like in the lecture, there are a lot of examples about different type of estimators. But like the thing I want to emphasize here is that so there are estimators that are unbiased but consistent, and there are also estimators that are consistent but not unbiased. So basically, like there are like kind of a trade-off between these two the property of unbiasedness and the property of consistency. So here we will work through a few different examples of identifiability of a statistical model. So first we have a Bernoulli statistical model. So the parameter here is just like the Bernoulli parameter Q. So this the dimension of the parameter is 1 because we only have one parameter. And so the parameter for a Bernoulli random variable is identifiable because if we have we can like show through like example, if theta not equals to theta prime, we would have p theta not equals to p theta prime as well. The second example we have is a Gaussian statistical model here with the mean as a being cosine of theta. So here we have two parameter. One is the theta, the mean theta, and the other one is the variance sigma squared. So those are the parameters for the Gaussian statistical model. And since we have two parameters, the dimension of the parameter will be 2. And does anyone want to tell me if the parameter is identifiable or not? So remember like the, since our mean will be like cosine theta, and remember like how the cosine theta looks like, it's like something like a wave. So we'll have like multiple, for multiple theta, we would have like the same density function. So in this case, like cosine theta would equals to cosine 2 pi plus theta. So there would like no way that we can actually recover like a true value for theta. So in this case, we would say like this parameter is not identifiable.
If the possible values of theta was bounded from like 0 to 2 pi, would it make it identifiable?
Yeah. In that case, that would be like identifiable if we put like a restriction on theta, maybe from 0 to 2 pi. Yeah, that's a good question. Yeah.
Thank you.
So the next part I want to cover is confidence interval. So confidence interval is like the way that we construct like an interval that would contain the true population parameter. So there are 3 ways to find a confidence interval. So in most sense, like if we take the population, the sample mean as a example, the confidence interval for the population mean would be like, so this is the sample mean, it would be like X bar plus minus some confidence level here. So if your confidence level is alpha, this part will be like Q alpha over 2 times some parameters that depend, like which we don't know here, divided by square root of n. So this 3 type of methods just tell you different ways to estimate this function of the unknown parameter here. So the first one is a conservative method, which we just plug in the maximum value for this function in to be like so the maximum value for this function we plug into this to replace this unknown value here. So we get like a really conservative bound in this case. And the second one is the soft method, which a little bit more precise, but like also like you have to solve like a quadratic equation of the thing smaller than some value t. And the last one is the plug-in method, which is like kind of you replace this unknown parameter with the sample estimate. So if this is like the population standard deviation, you just replace it with the sample mean standard deviation. So those are the 3 types, just to like convert this thing to like a proper rate confidence interval. The next one will be like delta method. So basically delta method helps us to find the asymptotic distribution of some transformation or like a function of a asymptotic normal random variable. So essentially, if we have like a asymptotically normal random variable, Cn, where like the asymptotically normal is about theta, we could find Cn, we would have like this function g of Cn would also be asymptotically normal about about g theta here, where we can where the asymptotic variance is defined as the first derivative of g prime theta and the square of this thing times the original sigma here, sigma square here. And there's like a important assumption about this part where we assume that g of Cn is asymptotically g of Cn is continuously differentiable at sigma and at theta. So this just means like we have like a first derivative at g of theta at theta, and this thing doesn't equal to 0. Next, we will do like a an exercise on the method of moments estimator, which we haven't reviewed yet, but like we can just review in this section. So the first question is, what does it mean for an estimator to be asymptotically normal? So we already talked about this. So essentially, this is just if we have an estimator theta. So theta should be like the square root of n times theta hat minus theta should converge in distribution to a normal random variable with mean 0 and sigma theta squared. And the second part of that, if we have a exponential random variables for some unknown lambda greater than 0, and g of lambda is the expectation of the exponential variables. This question asks us to find an expression for g lambda. So remember, if we want to calculate the expectation for a continuous random variable, so this will just we just take an integral of the density function of fx times x, integrate over the support for x, and the density function for exponential variable is just lambda times e to the power of negative lambda x times x here. And the thing is just like 1 over lambda. So this is like the first moment for an exponential variable. So the next question asks us to use the method of moments estimator to find an estimator for lambda. So essentially, like the method of moments estimator just use like the inverse of the moments function, and we plug in the first moment and the empirical first moment up to the d moment if we have like a d dimension random variable, and we've used this function to solve for the unknown parameter. So in this case, we want to find like a moments estimator for the lambda here. So we already know that we can calculate the expectation of the sample mean, which is just like 1 over this thing, and we know this this thing is equals to 1 over lambda, and then this is just equals to from like the law of large numbers, this is just like converged to the expectation converge, the sample mean converge to the population mean. So we would have x bar equals to 1 over lambda, and an estimator, a methods of moments estimator would just be x bar over 1 over x bar. So in the next part, we want to use the delta method to show that this estimator is actually asymptotically normal. So remember from the delta method, if we have we apply a function g on the estimator, we can say that this thing converging distribution to mean zero and g prime theta sigma theta squared. And first, by law of large number, we know that this estimator should converge in probability to lambda. And so we have something in the format of 1 over x bar. So we want to so our g function here is actually 1 over x. And by the central limit theorem, we have the xn bar minus 1 over lambda converging distribution to some mean zero and lambda sigmas 1 over lambda squared. So this is like the variance for the exponential variable. And since we have this part is like 1 over lambda, but what we really want is like something like lambda. So this is a part we can actually apply the delta method. So we know like if we have something that calculate the inverse of the reciprocal of a function, we could like recover lambda here. So this leads us to choose the g function of 1 over x. And then like if we want to use the delta method, we need to calculate the first derivative of this function at 1 over lambda. So this is just we know like the derivative of 1 over x is just 1 over negative 1 over x squared. And we need to also plug x equals to 1 over lambda here. And this leads to negative lambda squared. And so if we plug it into here, this will just be like 0. This is lambda squared, negative lambda squared to the square. And we also need to time the multiply the original variance we have, which is 1 over lambda squared. So this leads us to like a normal distribution with asymptotic variance lambda squared. So is this part clear? So our next step would be to use a plug-in method to actually find the asymptotic confidence interval for the lambda. So this like from above, we already know like lambda hat minus lambda would be smaller than Q2 over alpha over 2 times lambda divided by square root of n. So this would like, if we just break out this absolute value, we would have like the estimator is bounded by, is upper bounded by lambda times 1 plus q2 alpha over 2 divided by n, and lambda 1 minus q alpha over 2 divided by square root of n. And this is not like a true confidence interval because it actually contains like an unknown population parameter lambda. So the most simple way to find a confidence interval, a valid confidence interval in that case, is just to use the plugin method, where we just replace the unknown lambda with sample estimate. So we just add a hat here. So this will be like estimate from sample. So this is just like how the plugin method works, where we just replace an unknown parameter with an estimation of the parameter. So so in this course, we talk about like a few different estimators. And among them, the most well-known and like the most widely used is the maximum likelihood estimator. So if we want to find the maximum likelihood estimator, the first step would be just compute the likelihood function. So the likelihood function is just given samples x1 from xn and the parameter theta. This is just the product from of each individual density function. If the density function has parameter theta, and we plug in the observation xi here. And if we want to find the maximum likelihood estimator, this is just like an argmax on this likelihood function, where we denote the maximum parameter we find is sigma theta hat MLE. So I also want to cover about like something important is feature information. So the feature information is just defined as the negative minus expectation of the Hessian of the likelihood function. So the Hessian is basically just like the second derivative. So it's also equivalent to the second derivative here. So the feature information is used for the asymptotic normality of the maximum likelihood estimator. So before we dive into that, I want to first cover a few important properties for the MLE estimator. So the first one is consistency. So for MLE, we have that the MLE actually converge in probability to the true parameter. And the second property we have, which is really nice, is the normality property for the MLE. So this states that the MLE estimator convergent distribution to minus theta convergent distribution to a normal random variable with mean 0 and 1 over the Fisher information. So this can be calculated from here. So there is like two important assumptions about the asymptotic normality of MLE. So the first one we have is that the support of the support of random variable shouldn't depend doesn't depend on theta. And later we will see like an example of a uniform random variable where we wouldn't really have the asymptotic normality results. And the second one is theta is identifiable. And there are like a few more important assumptions, which we won't cover in this course because they're like a little bit too technical. And so why would we want to use something like MLE? So what's compared to the methods of moments, there are a few advantages of MLE. So the first one is that MLE is like more accurate. So the accuracy here is measured by the quadratic race. So basically it says that MLE has like a has less quadratic race compared to the methods of moments estimator. And the second nice thing about MLE is that it's really stable even if you have a misspecified model. So if you misspecify a model, you should still like recover a decent estimation from MLE. And if MLE is like really that great, why wouldn't we use it all the time? So it turns out like that MLE is like not always trackable. So in some cases, it would be like really hard to compute the maximum likelihood. So in that case, we might use like something that is like something like methods of moments, which we can always compute like a solution in that case. So we can first do like a walkthrough on an exercise of MLE for uniform distribution. So the first step about like if we want to find most maximum likelihood estimator for distribution, the first step would be to compute the likelihood, which is like the product of the individual density function. So for uniform random variable, we know that the density function is 1 over theta. Just ignore the star here. If our random variable is uniformly from 0 to theta. And then we also need to put like an indicator function here to ensure that the range of the support of our random variable is from 0 to theta here. And then the likelihood function is just a product of this. So likelihood of x1 to xn given theta is a product of the individual density function. So in this case, we will just have 1 over theta to the n squared, and this indicator function to the square to the power of n. So obviously we want to simplify this a little bit. So if you see something like an indicator function to the nth power, would be like very useful to think about like how could we replace this with the maximum or the minimum of the n random variables. So in this case, if we want like this our random variable to be between the range of 0 and theta. So this would be like equivalent to the minimum of those n random variable to be greater than 0 times the indicator function of the maximum of those random variable to be less than theta. And the support of the xi to be greater than 0 is already implied by the uniform distribution. So this thing is like always equal to 1, so we don't really care about this. So after get rid of this, essentially our likelihood is just like 1 over sigma to the nth power times the maximum of xi is smaller than theta. So this is a likelihood function. And if we want to find the maximum likelihood estimator, so in most of the cases, we could just take the derivative and find the extreme value. But in this case, since this is like not really easy to do like a derivative, what we can do is like maybe to argue from just plotting this variable. So here our y-axis is like 1 over maximum of xi to the square root. And our x-axis is maximum xi. So essentially we want this indicator function to be 1 if we want to maximize this function, right? Because if it's 0, we will like just get like a really small value. So if we want this to be 1, this would require theta to be greater than the maximum over xi. And we also know that this 1 over theta to the nth power decreases if we increase theta. So we want what we really want is to make theta exactly to be equal to the maximum of xi. So here the maximum likelihood estimator is just maximum over the x1 over xn. So does anyone want to tell me if this is asymptotically normal? We already talked about this. So this won't be asymptotically normal because remember that from one of the requirements we have from applying the asymptotic normality is that we need the support doesn't depend on theta. But here the support for the random variable is from uniform 0 to theta, which actually depends on theta. So in this case, the asymptotically normality won't apply here. So as for the next exercise, we will see like where we can actually apply asymptotic normality and find the asymptotic variance from future information. So this part, we will actually find the most likely maximum likelihood estimator for exponential distribution. So remember that the density function for exponential random variable is f lambda x is equal to lambda e to the negative lambda x, where we also require that x is greater than 0. And as the same idea, with the same idea as before, we can also replace this condition here with a density function. So this is with the indicator function. So this will be just the indicator function of x greater than 0. And again, if we want to calculate the likelihood, this is just a product of the individual density function, where we have lambda to the nth power e negative lambda summation over x1 to xn. And we also have the product over the indicator function here. So it's the same idea before. We can replace this with the indicator function of the minimum of xi greater than 0. So this would like require every individual random variable to be greater than 0. And for a lot of the case, one of the more handy format that we can work with is that we can work with the log log likelihood. So if we have like exponential here. So log likelihood just basically we can take the log with respect to the likelihood here. So this would turns out to be n times log of lambda minus lambda summation from 1 to the 1 to n xi. So this format is easier to do to take the derivative. So if we take the derivative of the log likelihood with respect to the parameter lambda, we would have n over lambda minus so this lambda just cancels out. This would just be like summation from x1 to xn. So we want this thing to be equal in order to find a solution for the maximum likelihood estimator. So if we just solve this equation here, this will just turn out to be the lambda MLE just equals to n over summation xi to xn. So this is like the maximum likelihood estimator for exponential distribution. And so since we don't have like the problems with uniform anymore, with a uniform distribution anymore, we could actually apply the Fisher information to find the asymptotic variance for the MLE here. So remember the Fisher information is just like the second derivative. So if we take the second derivative of the likelihood, we would have n over lambda squared. And in this case, we can just say that the MLE is asymptotically normal, where we have this minus the lambda, the parameter lambda converging distribution to a normal random variable with mean 0 and 1 over the Fisher information, where the Fisher information is just a thing. So this would just be like 1 over the second derivative, which is just minus lambda squared over n. So this is just like the two examples where we can calculate the most some MLE for uniform distribution and exponential distribution. So the next topic I want to cover is hypothesis testing. So generally, like hypothesis testing just help us to find the probability of observing some data with one hypothesis relative to another hypothesis. So there are a few very important concepts with hypothesis testing. So the first one is one sample test versus two sample test. So essentially, so for one sample test, we're testing against a benchmark. So this would be like maybe we want to test if some parameter is equals to 1/2 or not. And in the two sample test, we want to compare two unknown parameters to each other. So this would be a case, maybe we want to measure P1 equals to P2. So I will first talk through like the general recipe for doing like a hypothesis testing. So when we want to do hypothesis testing, we will first start with like specifying the null hypothesis and the alternative hypothesis. So we'll often use H0 to represent the null hypothesis, and H1 to indicating the alternative hypothesis. And after we specify the null hypothesis and the alternative hypothesis, the next step will be trying to design a test to decide between the null and alternative hypothesis. So this will where we will also often have like a test statistics. So a test statistics would just be like a binary thing between that takes value either 0 or 1. So normally if this test statistic is 0, we would not reject the null hypothesis. And in the other case, if we have the test statistic to be 1, we would actually reject the null hypothesis. And this test statistic is really defined with an indicator function where we have the sample minus this is like the parameter we want to test against, divided by like the variance of the distribution. The square root of the variance, which is the standard deviation of the distribution, is greater than C, some threshold C. So this part is just like an application of the central limit theorem. And after we standardize the random variable, we would want to compare it with a standard normal Gaussian variable, and based on the threshold we pick, we would use it to reject or accept reject the null hypothesis or accept the null hypothesis. So how should we pick this threshold? So suppose we have some given asymptotic level alpha. We want to choose like a threshold where we would achieve this given asymptotic level. So if we have if the asymptotic level is alpha, this would indicate that we use a threshold of Q alpha over 2 here. So another important concept is the type 1, type 2 error. So after we conduct the hypothesis testing, there are two ways that things could go wrong. So the type 1 error indicating that we reject the null hypothesis when it's actually true. Let me actually clean this part. And use a table to show this. So if our if in reality we have H0 and H1, and our test, if H0 is in reality we have H0 and our test also show H0, we don't have like any problem. So this is the same case for H1. But like if in the reality we have H0, but we actually reject it and accept H1, this will be like the type 1 error. And in the other case, in reality, if we have H1, if H1 is true, but we didn't reject H0, this will indicate we have like a type 2 error. So there are like a few different ways to conduct a hypothesis test based on different assumptions on the distribution. If you have like unknown variance or known variance. So they're like in the course we cover like I think 3 different tests. The first one is wall test, and the second one is likelihood ratio test, and the third one is implicit hypothesis test. So those are kind of important, but like I don't have time to actually cover it here. But like I think it would be like important to also review the assumptions and like the procedures for each individual test. So here we have an exercise for doing hypothesis tests for coin flipping. So this is like the most common example where everyone use like improbability. So basically in this test, we want to test if we have a fair coin. So we flip this coin n times and measure the proportion of time that the flips has like a heads come up. So we have we specify our null hypothesis as that we have a fair coin where like the proportion is equal to 1/2. And the alternative hypothesis is that P doesn't equal to 1/2. And we want our test to have a level alpha. So assuming the null hypothesis is true, what is the approximate distribution of P hat as we have n tends to infinity? So if we assume the null hypothesis is true, we can actually apply the central limit theorem, where we have we can first compute the test statistical, where we have the square root of n, the sample average minus the null hypothesis here, divided by the variance of the standard deviation of the Bernoulli random variable, because the coin flip is like a Bernoulli experiments. So this just be 0.5 times 1 minus 0.5. So this will be like our approximate distribution. And from central limit theorem, we know this should be like converged to like a normal random variable. And the second part asks us to write to find the rejection region of a test with level alpha. So just to review, so the rejection region is the part that we have the psi equals to 1. And since our test level is alpha, this thing should be like less than alpha. So this is the case that we reject the null hypothesis. So this is like the rejection region. Sorry. So to find the rejection region, we want psi equals to this test statistics greater than the Q alpha over 2, where we just have the absolute value of xn minus 0.5 divided by 0.5 times 1 minus 0.5 is greater than Q alpha over 2. So that's indicating that we have two parts of the rejection region. And this will be like x, and if we just simplify this and pull xn bar out, we would have xn bar less than 0.5 minus Q alpha over 2 times this whole thing here. So this will be like the first part of the rejection region. And we also have like a union for like the upper bound on the rejection region, which is just xn bar greater than 0.5 plus Q alpha over 2. It's the same thing here. So the next topic I want to cover today is linear regression. So I think we talk about like the univariate case as well as the multivariate case in class. So I will start first from like the univariate case, where we have linear regression basically say that if we have like a pair of random variables xi and yi, we want to find like a where like we assume that yi has like some linear dependency on xi. So so in this case, our regression function would just be expectation of y given x equals to x. And we assume that this dependency is linear in the format of a plus bx. And one way to find a solution to the regression function is to use the least squares estimator. So the least squares estimator solve the problem that we minimize the true y minus the predicted y. The square of this, and this is just essentially y minus a minus bx squared. So I won't go over it here, but like if we want to find the argument here, we just take derivative and solve for a star and b star. And it turns out there's like a closed form solution for the parameter for linear regression, where we have b star to be covariance between x, y divided by the variance of x. And similarly, a star would just be expectation of y minus b star times expectation of x. So obviously this is like the theoretical assumption, but like in real life, we won't always see that there's like a linear dependency between X and Y. So in most cases, we might have some additional noise where we have yi equals to a plus b times xi plus some random noise. And so this is like the format for empirical linear regression, where we assume that the noise to be to have mean zero, and also the noise is not the covariance between X and the noise should be zero as well. And if we have these two assumptions, we can also find a solution for the empirical the least square estimator for the empirical linear regression. And it turns out to be that this estimator is just the empirical version of the theoretical linear regression. So basically we replace everything here with the its empirical counterpart. So the covariance between xy would becomes xy bar minus x bar times y bar divided by the empirical estimation for variance, which is x squared bar minus x bar squared. And similarly, for a hat, we would have y bar minus b bar times x bar. So I think so the linear regression is kind of restricted because we don't really have a lot of like linear function in real life. So this is a point where people invent something called generalized linear model, which kind of relax the assumption on linear models, as we've seen before. So basically, we didn't talk about like the multivariate linear regression, but basically in multilinear regression, we just replace everything with a vector. So this, we were assuming y given x follows a normal distribution with mu x sigma squared times the identity matrix. And the multivariate linear regression assumes that this dependency of y on x, which is just mu x here, should be linear in the sense that we have like a vector beta times the x. So the regression function should be linear of x. So this is a little bit like still restricted. So what the generalized linear model does is that, so first it's relax the first assumption where the y given x should be like a normal distribution, where this is actually replaced with the whole exponential family here. And second, it doesn't really require that mu x to be like a linear function, in the sense that it only requires that there is like a mapping on this mu x. So this mapping, after apply this mapping, we should recover like a linear function. And this function g here is called a link function. I think that's everything I want to cover in terms of the concept for today. Wonder if people have like any specific questions, or maybe we can also work on like a few exercises. Okay, so maybe we can work on like an so in this case, like what I have talked about is more like focused on univariate case, but in the course we also cover about like multivariate case, where we have like extension on the central limit theorem as well as the delta method. So maybe we can work on a problem using multivariate central limit theorem. So essentially the yeah, actually that's an empty page. So the multivariate central limit theorem extend the univariate central limit theorem, where we can our X here could actually be like a random vector with dimension D. And assume that the covariance matrix of this random variable, a random vector, is sigma here. And the multivariate central limit theorem states that the square root of the mean vector minus the true mean should converge in distribution to a multi-dimension normal distribution with mean 0 and sigma, and the covariance matrix. Okay, so now suppose we have x1 to xn to be an IID Bernoulli random variable with parameter p. And we also have y1 to yn, also IID Bernoulli random variable, but with parameter q. And we also assume that these two random variables are mutually independent. So in this exercise, we want to find an asymptotically normal estimator for p plus q using the multivariate CLT and the delta method. So just to make it notation-wise simpler, we can define like a new random variable Zi, which is just like it contains xi and yi in each coordinates. And the covariance of this Ci so remember the covariant matrix in each entry we have the covariance between x and x, the covariant between y and y. And here this is the covariant between x and y. So the covariance between x and x is just the variance of x. And this, because we know that these two things, we already assumed that x and y are mutually independent. we would have the covariance between xy to be 0. So the covariance matrix for Z would just be P times 1 minus P 0 and Q times 1 minus Q. So after we have this, we can just use the multivariate central limit theorem to find the asymptotic distribution where we have xn bar minus mu convergent distribution to 0 and sigma. Where this sigma is just like the asymptotic asymptotic variance. So now we want to use the delta method to actually to give like a asymptotically normal estimator for the unknown parameter p plus q. To do this, we can define like a new function g of xy, where g of xy is just x plus y. So we can recover this p plus q here. And so in the multivariate delta method, we would have the function g of xy minus g of pq convergent distribution to this is like an extension on the previous second derivative for the univariate case. Where we have delta HPQ transpose times the covariant matrix times delta GPQ. And if we take derivative to the G function here, we would see like this just be like 1 because so the first component is like derivative to x, partial derivative to x. The second component is partial derivative to y, and we'll have like 1. So this leads to the first part to be 1 transpose times sigma 1. And we'll just have normal distribution with 0 and sigma here. So I think I have run out of problems. I think that's like all I have like I really want to cover for today. So I'm just wondering if people have like any specific questions. Yeah, I think the multivariate case, I would think like you shouldn't worry too much about it because it's like, I think in the exam we'll like mostly cover just like the univariate case. Yeah, but like that still like something that's like good to know So I think we got a question about the comparison between Bayesian MLE and Moments estimator. So the first thing about like, so both MLE and Moments estimator, they're kind of frequentist estimator where they don't assume any prior knowledge about the distribution itself. But like Bayesian, like in Bayesian estimation, we would actually impose some prior on our parameter. So like say if we want, I didn't cover Bayesian today, but like basically like we can assume that like maybe if we don't know anything, we can assume like a flat prior. And if we know something, we could like actually get like a more informative prior. And the likelihood for like, so like the updates in Bayesian is that like we have a prior and then we observe some new evidence. And we can update to get like a new posterior function. So in terms of the prior choose, you can get different posterior function, but like one handy family of prior is a conjugate prior, where you can so after you do the updates, you recover the same family of distribution for a posterior distribution. And in terms of the difference between MLE and Moments estimator, I think I have talked about it. But essentially MLE is like the better one if you your likelihood function is tractable. And it's better in terms of it has like a better accuracy and lower quadratic risk. And also it's like more stable in terms of if you specify your model incorrectly, you will still able to recover something reasonable for your MLE. But like in the Moments estimator, if your Moments function is not specified correctly, you won't be able to get like a very good Moments estimator. Yeah, I think that's mostly the difference between this three estimators. Any other questions? Another question is that asking if there are some examples using computation for like doing like a chi-square type hypothesis test. I don't have like an example with me right now, but I think there are like some examples in the lecture notes where like you can always review. Yeah. I think we also have a question about Jeffrey's prior. All right, I think I can do that part. Um, So we already talked about feature information, and Jeffrey Prior is something used in the Bayesian statistics. Basically, so Jeffrey Prior is proportional to the deterministic determinant of the feature information matrix. And most of the cases will only have like a single parameter. So this is actually just like equivalent to the square root of the feature information for single parameter theta. I think I have like an example of Jeffrey's Prior, but before like a previous session. But like maybe I can send you like if you're interested, I can send you like that particular example using Jeffrey Prior and reparametrization invariants. Yeah, I just don't have like a nice example with me right now. Any other questions? I think if we don't have like any more questions, maybe we can end the session a little bit earlier. Hi, Paula, are you still there? Yeah, I think people are kind of interested, like probably in more like exercise. I think that's like um a little bit hard to make up like an example right now, but I think like I can maybe forward to the organizer like a kind of like a worksheet for like the part with different hypothesis like chi-square test, as well as like the Bayesian estimation part. I think that'll be like super useful, like if we can kind of like just work through the problems on your own. Yeah, I think if there are like no other questions, probably we can just end the review session here. Yeah, I hope you guys like I hope like good luck on your exams. I hope like you have like a nice review session. Yeah.
Then thanks, Alicia.
Thanks. Bye.
Thank you.
Bye. Have a good night.
Thank you.